Okay, welcome to part two. In part one, we just finished proving once and for all that the derivative of the function f of x equals x cubed is 3x squared. We're going to move on now to a little bigger challenge and try to prove the derivative of x to the n for any power, and this will require a little machinery. A handy tool for doing this in particular cases is Pascal's triangle, discovered by Blaise Pascal. And notice how it works. I have ones here, and then in the third row, what do? I always start with a 1, and then in between I compute the total. 1 plus 1 is 2, and then a 1 at the end. To get the third row, I start with a 1, and then 1 plus 2 is 3, and then 2 plus 1 is 3, and then I end with a 1. In the fourth row, I start with a 1. 1 plus 3 gives me 4. 3 plus 3 gives me 6. 3 plus 1 gives me 4. And I end with a 1. And you can see the pattern repeats. Each term that's in between two terms above is the sum of those. So 1 and 4 is 5. Down here, 10 and 10 is 20. And I could keep going. What good is this? Well, what this triangle does, it gives me the coefficients in the expansion of x plus h, not just squared, but to any power n. For example, x plus h to the fifth, here's the coefficients: 1, 5, 10, 10, 5, 1. 1 times x to the fifth, 5 times x to the fourth h, 10 times x cubed h squared, etc. And the coefficients follow that fifth row, well, fifth useful row in Pascal's triangle. And notice what happens with the exponents. I start out with x to the fifth, because the whole thing is raised to the fifth. The powers of x keep decreasing: x to the fourth, x cubed, x squared, x, and then x to the 0 or none. And the powers of h keep increasing: h to the 0, not there, h squared, h cubed, h to the fourth, h to the fifth. And this will work for any x to the n as long as I use the coefficients for each of these terms generated by Pascal's triangle. But if I want to do something like x plus h to the 100th power, it's not practical to make 100 rows in Pascal's triangle. So there's a better way, a simple formula. It's called the binomial coefficient. The kth entry in the nth row of Pascal's triangle is given by the binomial coefficient n choose k. If you took statistics, you might have seen this. It's defined as n factorial divided by k factorial times n minus k factorial. And remember what a factorial is. N factorial is just n times n minus 1 times n minus 2 all the way down to multiplying by 1, the product of all those terms. So k factorial is just k times k minus 1 times k minus 2 down to 1, and n minus k factorial, I start at n minus k, multiply by n minus k minus 1, etc. So it's easier to see with an example. Suppose I do 6 choose 2. That would be the second entry in or the entry number 2. Actually, they start numbers with 0. We'll see that when we do an example. So it's that entry, 6 choose 2, is 6 factorial over 2 factorial times 6 minus 2, or 4 factorial. Well, there's 6 factorial. 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. And 4 factorial, 6 minus 2 is 4. 4 times 3 times 2 times 1. Well, notice the 4 times 3 times 2 times 1's cancel out. I'm left with 6 times 5 over 2 times 1. Well, that's 30 over 2, or 15. So that 15 is, if we go back to Pascal's triangle, there we call that entry 0, entry 1, entry 2. That's the entry corresponding to h squared in Pascal's triangle. And notice that by formula, n choose 1, that would be the second entry, is n factorial over n minus 1 factorial. Well, that's n times n minus 1 factorial. And the n minus 1 factorials cancel. You can show for yourself that that always is just n, because the rest of the terms in the numerator will cancel the entire denominator. And n choose n, the last term, is n factorial over n factorial times n minus n factorial. That's just 1 because we define in probability, and anywhere we use factorials, we define 0 factorial to be 1 to make these formulas work. So using the binomial coefficient, we can expand x plus h to the n as follows. It's 1 times x to the n, and then n choose 1, which is n, times x to the n minus 1 times h. The next term is n choose 2, and then x, the power of x gets reduced one more, n minus 2, and the power, or the exponent of h, goes up to 2, all the way down to the last two terms. N choose n minus 1. If you work that out, it's also going to be n, and I'll have just a single x to the first power and h to the n minus 1, and then n choose n, or 1, times h to the n. So this is the replacement for the coefficients in Pascal's triangle. We can compute them directly using this factorial formula. In fact, most calculators have n choose r as a function, so we can compute this directly. But we're going to use this to prove that the derivative of x to the n, well, we'll see what it is when we get there. So notice carefully, if I want to compute the derivative of x to the nth power, where n is some positive integer, then we let f of x be x to the n. The derivative is the limit as h goes to 0 of x plus h to the n minus x to the n, all divided by h. Well, we can use the binomial expansion we just showed on the previous page. What happens when I expand x plus h to the n? I get x to the n plus n, that's n choose 1, times x to the n minus 1 times h. We bring in the first power of h. And then n choose 2 times x to the n minus 2. The power of x goes down one more, and h squared, all the way down to h to the n. That's the last term in this expansion. And then remember, we subtract f of x, so that's x to the n. Notice, as usual, as in the previous examples, I have a minus x to the n and x to the n. Those terms cancel out to 0. So the first term remaining is n times x to the n minus 1 times h, plus the rest of the terms, down to h to the n. All of these have an h in them, so I can factor out the h and cancel it under the protection of the limit. So notice what happens now. Because this term had h to the first, and all the others had higher powers of h, just like we saw when we worked out the expansion of x plus h cubed, all these remaining terms except for the first one are still going to have an h in them to some power after I cancel h over h. So this becomes the limit of n times x to the n minus 1 plus n choose 2 times x to the n minus 2 h, all the way down to h to the n minus 1. Well, this still looks like a polynomial in h. I can plug in h equals 0, and all the other terms go out. I'll get x to the n times x to the n minus 1 plus this first term has an h in it, so that multiplies to 0. All of these other terms still have h's in them, so they'll all become 0 when I multiply by h to some power. And the only thing that's left is that first term, x to the n minus 1, or n times x to the n minus 1. So we've done it using this idea of the binomial expansion of x to the x plus h to the n. We've proven that the derivative of x to the nth power is n times x to the n minus 1. So in practice, all we need to do to compute the derivative of x to any power is bring that power down in front and subtract 1 from the exponent, as we've shown here. Let's see how it works. Some examples. What would be the derivative of x to the fifth? Well, it's 5 times x to the fourth, n times x to the n minus 1. What would be the derivative of x to the 17th power? Well, it's 17 times x to the 16th, n times x to the n minus 1. What would be the derivative of x to the 124th power? I'd hate to expand that out by hand. It's f prime of x is 124 times x to the 123. So we can use this now to compute tangent lines. For example, if f of x is x to the fourth, and I want to determine the equation of the line tangent to the curve at x equals 3, I don't need limits anymore. I know how to compute the derivative of x to the fourth, and that tells me the slope of the tangent line. So the derivative of x to the fourth is 4 times x cubed, that's n, times x to the n minus 1. So the slope of the tangent line at x equals 3 is simply the derivative evaluated at 3. That's one of the reasons we use the derivative. Well, the derivative is 4x cubed, so this is 4 times 3 cubed. 3 cubed is 27, 4 times 27 is 108. So 108 is the rate of change of this curve at x equals 3, which is the slope of the line tangent to the curve. But to get a line equation, I also need a y-intercept, and to do that, I can simply use a y value minus m times the corresponding x value. Well, all we had was an x value, so we need to find the y value that goes with it. We do that on the original curve, right? So to find the y value, I need to compute f of 3, which is 3 to the fourth, using the original function. So the y value that goes with x equals 3 is 81. That tells me that the point 3, 81 is on the curve f of y equals f of x, y equals x to the fourth. So now we have a y to go with our x, and the b is y minus m times x. So 81 minus 108 times 3. Calculator will show you that that's minus 243. So that's my y-intercept. So now we've found the tangent line equation. It's y equals mx plus b. Y equals 108x minus 243. And we have it pictured here. Notice the tangent line at 3. The height of the point is about a little over 100, right? No, actually it's 81. Yeah, so this is y equals 81. The slope of the line is 108. You can see the y scale and the x scale are very different. And the y-intercept is down here at minus 243. And that looks like a tangent line should look. It just touches the curve at that point. Okay. So now we can move on to the derivative of a polynomial. A polynomial is in general a constant plus something times x plus something times x squared plus something times x cubed all the way down to something times x to the n for some particular n. It might stop at x to the 10th or x to the 50th or x to the 984th, whatever. They're all polynomials. Well, if we have a polynomial of this form, we already know what the derivative of the first part is. The derivative of a constant plus something times x is just that multiplier of x. And now we can take the derivative of the next term. We know it's the derivative of x squared is 2x, so the derivative of this whole thing is a2 times 2x, or 2a2x. The derivative of x cubed is 3x squared, so I include the term a3, and there's the derivative of the third term all the way down to the last term. It's the derivative of x to the n is n times x to the n minus 1, and we still have that constant multiplier. Why does this work? Why can we chop it up like this? Well, two important limit rules that we went over last week are the following. The limit of the sum is the sum of the limits. That is, I can take the limit term by term and add up. I use that here. I'll take the limit of the first term, the limit of the second term, the limit of the third term. Well, why does this work? Well, the derivative is a limit. It's defined through the limit, so it inherits these properties of limits. So the derivative of the sum is the sum of the derivatives term by term. And also, we learned we could factor constants out of limits. So because the derivative is a limit, we can factor the constants out of the derivative. So the derivative of a2x squared is a2 times the derivative of x squared, as we used to get this formula. Let's look at some examples. If f of x then is this polynomial 5x squared plus 3x plus 2, then the derivative is 5 times the derivative of x squared, 5 times 2x, plus 3 times the derivative of x, which is 1, or the derivative of 3x is 1, and the derivative of 2 is 0. 5 times 2 is 10. So the derivative of 5x squared plus 3x plus 2 is simply 10x plus 3. Again, now that we have a nice rule for the derivatives of x to the n and extending that to polynomials, we don't need to use the limit definition to compute derivatives in this special case. Here's another example. F of x is 8x cubed minus 11x squared plus 8x plus 5. Well, the derivative is 8 times the derivative of x cubed, which is 3x squared, minus 11 times the derivative of x squared, which is 2x, and then the derivative of this last piece is just 8. So 3 8s are 24. This is 24x squared minus 22x plus 8. Easy, right? Now that we have a rule to use. Your turn. So for these 4 cases, please do the work. Find the derivative of x to the 7th. Without using the limit definition, you can now use the rules we developed here. Find the derivative of 3x to the 4th. Find the derivative of this polynomial, x cubed plus x squared plus 1, and then use our definition of the derivative of a polynomial to compute the tangent line on this curve at y equals 2x squared minus 3x minus 4 at x equals 3. And then use your calculator to plot the curve and the tangent line, verify your results. So I'll pause the video here and you can do the work. Okay, so hopefully you found that not too difficult. You paused the video, you worked these exercises. Let's compare answers. So if f of x is x to the 7th, by my rule for the derivative of x to the n, f prime of x is just 7x to the 6th. If f of x is 3x to the 4th, then by my rules above, the derivative is 3 times the derivative of x to the 4th. That's 3 times 4x cubed, or 3 times 4 is 12, that's 12x cubed. For this polynomial, I take the derivative term by term and add them up. The derivative of x cubed is 3x squared, plus the derivative of x squared is 2x, and the derivative of x plus 1 is 1. Now for the tangent line case, my function, which gives me my y values, is 2x squared minus 3x minus 4. So the derivative is 2 times 2x minus 3, or 4x minus 3. At x equals 3, we can compute the y value that goes with it. So at x equals 3, we plug into the original equation. Y is 2 times 3 squared minus 3 times 3 minus 4. Arithmetic shows that that's 5. So the point 5, 3 with coordinates 3, 5 is on the curve. And now we can use the derivative to find the slope. So m is f prime of 3, the derivative evaluated at 3. Well, the derivative was 4x minus 3. So evaluated at 3, that's 4 times 3 minus 3. 12 minus 3 is 9. And I can get the corresponding intercept using my point. Y minus mx gives me negative 22. So the tangent line has equation 9x minus 22, and if you plot them, they should look about like that. At 3, the curve has height 5, so that point is the point 35. The slope of the line is 9, we found using the derivative evaluated at 3, and the y-intercept is minus 22, and there it is right there. Okay, so that's our work for the week. On Monday, we'll have a quiz on basic derivatives using the limit definition and also our new work here. Later today, I will post a quiz on derivatives to D2L. Please complete this quiz before class on Monday.